Okay, so if T1 sends R, what will the receiver play? B. Sender receiver, because the receiver's payoff are 2P plus 1 minus 2P. Right? His payoffs from sending A are 1P plus 0. Right? So we'll pay B. If he plays B, what does the receiver, what does the sender get? What does the T1 sender get? If he plays B, the sender of type T1 gets 0. Whereas if the sender of type T1 plays L, what does the sender of type T1 get? If it plays L, what does what does the receiver get? A, right? A. So what does the sender of type T1 get? 1. So the sender of type T1 is better off sending L. Right? So then, right? RR is not the possible PV. So think of find out all the other perfect Bessel equilibria. This is an important sum. So far we have used to sum which are mechanical. So if I give you a Coulomb game, you know how to take derivatives, set it equal to 0. There is nothing like that here. Right? All that has to happen is here. So please. Okay, so tell me whether T1 sends L and T2 sends R. Is there a separating equilibrium? Is separating a perfect Bessel equilibrium? Separating where T1 plays L and T2 plays R. If T1 plays L, then Q is equal to 1, P is equal to 0. Those are the values.
P is equal to 0.
And if P is equal to Q, if T1 plays L, then P is equal to 0. L, then P is equal to 0 is the correct value.
Yeah. So if P is equal to 0, then we will play T1 when P is equal to 1, then P is equal to
Arey Baba, because T1 plays L, Q is equal to 1 and P is equal to 0. It is not, you don't have to specify P and Q before. P and Q are rational beliefs from observing things.
But 0.5 probability that receiver will get
0.5 okay. T1, if you observed L and you know that T1 plays L and T2 plays R, then you are sure you are here. So Q is equal to 1 and P is equal to 0. These are different probabilities from that. These have to come from base rule. These have to come from base rule. So if T1 plays L, which means Q is equal to 1, right? If Q is equal to 1, what will the receiver do then? He will play A of it. Okay, right? Okay, let me change this game a little bit by making it a bit simpler by making this number 2. 4. Okay? Let me make this 4. Okay. So what will the receiver pay? B. So what is the payoff for the sender? 3. By playing L, right? If he unilaterally deviates, if he plays R, and the receiver keeps on playing A, then what are the payoffs for the sender? 1. So the sender will not unilaterally deviate. Right? The sender will not unilaterally deviate. Similarly, what do you think of, so sender of type T1 will be better off sending L. What would be the sender of type T2 do? Will he send R or L? R or L? Because then Q is equal to, so he knows he's here. He knows he's here. If he's here, what will the receiver play? B. Right? Okay. And so what are the sender's payoffs? If he plays L and the receiver continues to play B, then what are the sender's payoffs? 3. So what is he better off doing? L. And so therefore, LR is not the perfect Bayesian equilibrium. Okay. So is there a pooling equilibrium on LL? Is there a pooling equilibrium on LL? Yeah? So LL is a perfect Bayesian equilibrium. Pooling on L is a perfect Bayesian equilibrium in this game. Pooling on L is a perfect Bayesian equilibrium in this game. Here, समझा कैसे निकालने का perfect Bayesian equilibrium? You have to think through, right? पक्का समझ रहा? Okay. Yeah? So what is the are there any other perfect Bayesian equilibrium on this game? Say pooling on L and R. So can you think of R and L as a separating equilibrium? So player 1 chooses, T1 chooses, sends R and T2 chooses L. Is that the separating equilibrium? Perfect Bayesian separating equilibrium? Because in which case P must be equal to 1, Q must be equal to 0. Right? P must be equal to 1, Q must be equal to 0. If P is equal to 1, what is the receiver doing better off? A. No, B. B. Right? So if the receiver is going to play B, is T1 better off sending L? Yes. Right? And therefore that cannot be a separating equilibrium. Right? So T1 sends R and T2 sends L cannot be a separating equilibrium. Okay? Right? ठीक है? Everyone understood this?
So when we are getting equilibrium, basically getting it from not having a separating equilibrium. But in the previous sum, we actually rejected the other equilibrium.
No. In the previous example, we had one separating and one pooling equilibrium. In this case, we just have one pooling equilibrium. You can get more than one separating equilibrium, more than one pooling equilibrium also. Right? For example, if I change the number of actions that the receiver can take. So the number of actions that the receiver can take are R1, R2, L1 and L2. Okay? Or number of messages that the sender can send are R1, R2, L1, L2. And the number of actions that the receiver can take is A1, A2, A3, A4. Then you will get a more complicated structure. Right? But I don't want to, that would be really confusing you. But all that I want you to understand is the basic ideas between pooling and separating equilibria. Is this clear to everybody? Okay? Right. So that ends our module 2. Module 3 we have done partly already. Right? Now we have to introduce 2 or 3 more ideas in module 3. So I'll quickly do that right now. So I think by today's class or tomorrow's class will be end of module 3, then only one module remains. Right? Okay? Sure. But पक्का clear है ना ये? Okay?
So, give us 2-3 sums so that we can solve.
You have to solve it in class today?
We solve it.
Then I don't have to give. What do I mean by giving some? I can change those numbers, whatever I want. So change those numbers arbitrarily and sit through and work with that. Right? So practicing really, for example, if I ask you that these numbers are take this. Solve this. Find out all the cooling and separating equilibrium. Find all the perfect basic equilibrium.
So I wanted to write a systematically, then I have to get all the possibilities of expected payoff
You have to argue this. Why something will not be here? Yes, we have to calculate all the expected payoff and everything.
then I have even calculated, that means I will.
क्या बोलेंगे इसको? Even plays R, when the receiver observes that the receiver observes whether he is here or here. So the receiver gets 3 or 1. 3 into P plus 1 minus P, right? From playing A. And obviously 5P into 1 minus, right? Okay, so the way I have chosen the number irrespective of P is better of playing B. But the correct value of P is obviously 0.5 because you can write for if you're looking at a cooling equilibrium. Right? Okay? So you choose better of choosing B. If he chooses B, right, then the payoff from choosing R for T1 is 5 and for T2 is 7. Right? For T1 the payoff from choosing L is what? Right? So what is T1 measure of playing L?
Cooling strategy R. T1 will play R.
If T1 plays R, what does T1 get? 4. Whereas if T1 plays L, what does T1 get? 5. So what will the T1 send? L. So T1 will send L. What will T2 do? So if T2 sends R, okay, what will the receiver do? Receiver will choose B, irrespective of whatever P is. Right? Okay? So will T2 be better off choosing L given the receiver playing B? No. So therefore, what is the equilibrium? This is a separating perfect Bayesian equilibrium. T1 chooses L, T2 chooses R. The perfect Bayesian equilibrium is separated. Can you think of any cooling equilibrium on this? Why? What will happen if both players choose L? So cooling cannot be an equilibrium. Suppose I ask you whether T1 chooses L and T2 chooses R is a separating equilibrium. In which case Q is equal to 1, P is equal to 0. So you know you are here and then you have to evaluate, right? So if T1 chooses L, this person will play B. Right? So that's how you will get the separating equilibrium. If I ask you for a separating equilibrium, T1 plays R and T2 plays L, will that be a perfect Paschen equilibrium? T1 chooses R, T2 will choose B. Because P is equal to 1. Right? But in which case T1 will get 4, whereas by choosing L he can get 5. Right? Because for any value of Q it's sensible for player to choose B. So the receiver choose B, right? Okay, now why is this important? Okay, let me tell you a story. Okay, which you must now build into this. Okay? Suppose I am an employer. I want to choose an employee. What happens to the benefit to me depends upon how skilled the employee is. Okay? Right? About 70% of the employees are low skilled, 30% of the employees are high skilled. That is what I believe. I know. 70% of the employees are low skilled, 30% of the employees are high skilled in nature. Right? Okay. Now, once an employee is chosen, right? Okay, an employee who I hired can actually send me a signal of what? Of say, let's put it like this. No, actually we need to put more structure on this, so we'll leave this one. With this you can solve all these, right? So you're fine with this, okay? Right? So then, okay. So let's now go to the next module. How much more time do we have? Half an hour. So it's enough to talk about the next one, right? Okay. Now, you remember that when we talk about monopoly, we said yeah, marginal revenue is P into 1 upon 1 plus E, 1 plus 1 upon epsilon, like E is the elasticity of demand. Do you remember that derivation? Right? We also know that marginal revenue is equal to marginal cost, which means right, or right, notice P minus MC, the gap between price and marginal cost. So profits per unit. What is P? The price. So what is P minus MC upon P? The profits per unit as a fraction of the price. So we are charging the price equal to 100 and the profits per unit at 10, then P minus MC upon P is 0.1. Right? The stronger monopolist you are, the greater is your ability to put a gap between P and MC. Right? So this measure, this quantity, P minus MC upon P, measures how powerful a monopolist you are, or it's called the Lerner index of monopoly power. Okay, Lerner index of monopoly power. The Lerner index of monopoly.